Okay, so now I'm going to talk about power series. This is going to be kind of a longish video because there's a lot to get through as we get started here. So you can think of a power series as an infinite polynomial. Okay, so this is what they're going to look like. So you're going to have, right, a summation. We're going to start at 0 just because we, right, take everything into account. We can maybe have a constant term. And then you're going to have this a sub n. Now, you don't want to think of this, well, I mean, it might be just a coefficient, but right, it's probably going to be like one of our series that we've been talking about. So this a sub n coefficient is going to be changing with n. Okay, so right, we would have a sub 0, x to the 0 is just 1, right? And then we'll have some other, right, coefficient that may have n's in it, right? And then x to the first, and then a sub 2, x squared, right? And some third x cubed, and so on. It just keeps going forever. Okay. Or, right, it doesn't have to necessarily be just an x. It could be an x plus or minus some actual constant. So c would be a real number. And so this would look like, right, a sub 0 still, but then you'd have, right, a sub 1, x minus c to the first, and then a sub 2, whatever that might be, x minus c squared plus dot, dot, dot. Okay. Now that first one that I wrote, right, this would be an infinite series, a polynomial, a power series, centered at x equals 0. Okay. Versus that second one that I wrote, and that would be centered at x equals c, right? So thinking all the way back to your algebra 2 lives, right, that's just a shift. So a shift of our infinite polynomial. Okay, so for right now, it's going to seem like, well, why would I want to, right? Why would I go to all of this trouble? Well, we can use these infinite polynomials, and we will, to approximate other functions. So like trig functions or exponential functions, or things we can't even write explicitly. We can use these infinite polynomials to get a good approximation. Okay? Now, with that, right, now we have to decide, well, we have this power series. How good is it? And when we say how good, does it converge? Does it go to a value, right, as we add all of those up? So our power series, and I've done the generic one where we're centered at C, our power series will satisfy exactly one of the following. So it's going to fit into one of these three categories. So the series might converge only at x equals c, so only at the center. That this one position is the only place that it's not infinite, okay? And it diverges everywhere else. It might converge for all real numbers. There are some series that just do that, right? And the part, right, where we get to do some work this time is this third case. So remember our backwards e, there exists a real number r that's positive such that the series converges for all x minus c's, absolute value, that are less than r, and diverges if you're outside of that range. Okay? So you can sort of think of that on a number line, right? So, right, if x equals c, right, that's where we're centered around. So case 1, it only converges there at c. Case 2, it converges for everything on the number line. And for case 3, right, this would be c minus r, and over here would be c plus r, right? So your r away from c, and your x's would, right, your series would converge for any x value you pick in this interval right here. Now, and diverge on the outside. So, gets me to my parenthetical remark here. So notice I put my parentheses here. We're going to have to check those endpoints when x minus c equals r to know if they're included or not. So the r is called the radius of convergence, right? So that's just going to be right here, this value r that we find. And then the interval of convergence is going to be that x minus c, right, solutions to this inequality. So negative r less than x minus c less than r, So negative r plus c and r plus c. Okay. And then, right, so notice I've just left it with less than symbols. When we check those endpoints, we may put in equal signs on some of them, right? So our goal is going to be to find that r value, right? That's our first goal with our power series. Okay. So how do we find r? Great question. Well, we're going to use the ratio test. So the ratio test is going to help us decide what is r and what is I. So what is the radius of convergence and what is the interval of convergence? So let's just go over the ratio test one more time. So I have my infinite series from 1 to infinity of a sub n. And we're going to let rho, so I'm going to use a rho now. So this is my version of a rho. And so rho is the limit, right, as n gets big, of the n plus first term in your series over the nth term in your series. A sub n plus 1 divided by a sub n, absolute values. Right? So, and then remember, if rho is less than 1, then your series over here converges. If rho is greater than 1, your series diverges. And if rho equals 1, well, we don't know, right? That's going to be, right? That's those endpoints that we're going to be checking. Okay, so let's go ahead and practice. I have 3 examples. So let's find r and I for the following series. So this one I'm going 0 to infinity, x to the n over 3 to the n. All right, so we're going to write out the ratio test for this. So ratio test. So we're going to take, let rho equal the limit as n gets big. Okay. And then I do a sub n plus 1. So that's x to the n plus 1 over 3 to the n plus 1. Okay. Now then that's divided by, but remember I'm dividing by and it's going to be a fraction, so it actually flips and multiplies. So I'm going to just do it times. So when a sub n flips and multiplies, that'll put 3 to the n on top and x to the n on bottom. So rho limit n to infinity. So now I'm going to do some algebra, right? Those fabulous exponential properties that have been drilled into you forever. So x to the n plus 1, so it's kind of working backwards. So that's the same thing as x to the n times x to the first, right? And it's kind of hard to see until you've done a few, but multiply like bases, you would add the exponents. Okay. And we're going to do the same thing with the 3. So 3 to the n times 3, right? And you see what beautiful thing happens here. And don't worry, after you've done 2 or 3 of these, you will see that over and over, so it won't be that bad. Now you can go ahead and reduce, so cancel out those common factors. So 3 to the n's and x to the n's. Okay. We're getting closer, so I'm going to write one more time. Okay, probably more than one more time, but for now, one more time. So the limit as, right, n gets big. So what do I have left? I have x over 3. So now let's think about what the ratio test tells us. It tells us that as long as this limit is less than 1, then my series converges, right? Okay, so for what values? So notice my n is gone. So now it doesn't, right? My n's are all the way gone. So I can drop my limit, right? So now it's just, I need to know when absolute value of x minus 3 is less than 1. I can multiply my 3 across. Well, it happens whenever my x's are less than 3. Cool. So guess what r is? R is 3. That's our radius of convergence. Note, so my polynomial, I guess I could have written out a couple of terms. So we write out some terms. Sorry, I'm going to backtrack here. I'm going to circle my answer. This is our radius of convergence. Sorry, radius of convergence. So this polynomial that we had, so if x equals 0, I have 1 over 1. If n is 0. If n is 1, I get x over 3, and if n is 2, I'll get x squared over 9, and x3, 27, ... Okay. So this polynomial, if you look back on the first page, this is centered at x equals 0. So it doesn't have a shift at all. Okay. So my radius of convergence is 3. So now let's find that interval of convergence. So I'm going to take this inequality, right, that we just had, write this inequality here, and I'm going to rewrite it without the absolute values. So that would be negative 3 is less than x is less than 3. Okay. And now we're going to check our endpoints. So now we solve for x, and this already is. So now we're just going to check our endpoints. So does our series converge if x equals negative 3? Okay. So here's my series. So I'm just going to replace the x with a negative 3. Well, let's see. So now does the series n equals 0 to infinity, make sure I'm still on here, scooch. So x is going to get replaced with a negative 3 to the n over 3 to the n. Okay. Well, they're both raised to the nth power, right? So I could rewrite that as 1 ratio. So then I'd have negative 3 over 3 to the n. So that's the number negative 1 to the n. So what happens if I start writing terms there? What do you get? You get 1 if it's n is 0. The next one is minus 1, plus 1, minus 1, plus 1, minus 1, dot, dot, dot. My nth term doesn't go to 0, so it doesn't work. It does not converge if x equals negative 3. So I'm not going to include that one. Okay, so then let's check positive 3. Okay, so again, you're going to replace the x back in your series with a positive 3 and see what happens. So n equals 0 to infinity. X is going to be a 3 to the n over 3 to the n. Oh, well, now you're just adding up a bunch of 1s, just all positive 1s. So that's just 1 plus 1 plus 1. Again, it fails the divergence test. Maybe it passes the divergence test. It diverges, right? So I'm not going to include my 3 as well. So my interval of convergence, in whatever notation you're going to use. Oh, sorry. Interval of convergence. Say it and write it, right? Convergence. I almost wrote conversation too. Convergence. Oh my gosh. Negative 3 to 3. Not inclusive, so parentheses. Okay, let's do 2 more. I told you it was a long video. See if we can get some of the other cases going here. So here's my series. Maybe you can see where it's centered, right? Centered at negative 2. You could write out some terms if you wanted. So my first term is actually a 0 because I got 0 times. And so the next one, if n is 1, I'm going to get 1 times x plus 2. And now if n is 2, 2 times x plus 2 squared plus 3 times x plus 2 cubed plus, right, dot, dot, dot. So that's what that polynomial would look like, our infinite polynomial. So let's see, right, if we can find a radius of convergence. So we're going to use the ratio test. So here goes our ratio test. So I'm going to take, I'm going to set rho equal to the limit, n gets big. So I need the absolute value. So I need n plus 1th term, right, a sub n plus 1. So I'm going to get n plus 1 times x plus 2 to the n plus 1. Now remember what I did on that last example for the n plus 1. I'm going to have an x plus 2 to the nth. And then for the plus 1 part, I just get an extra x plus 2. Okay. Now, and then I'm dividing by a sub n. Right, and that's just this guy right here. This whole thing is my a sub n. So n times x plus 2 to the n. And now I want to know for what values of x, does this converge? Does the, let's say, is this less than 1? So go through and cancel out your common factors. So now we're going to take the limit of, I've got n plus 1, parentheses, I guess, x plus 2, and I've got an n in the bottom. And we're taking the limit as n gets super big. Right? And when is this less than 1? Okay, so as n gets big, so if we think about our limit, right, the x plus 2, this doesn't actually have the n in it, so that's just kind of along for the ride. So the n plus 1 over n, as n gets big, that whole thing goes to 1. So my inequality becomes, right, when x plus 2, the absolute value of x plus 2 is less than 1. Oh. Okay, well, so it looks like my radius of a convergence is 1. And now let's check our interval of convergence. So I obviously thought this was going to take less room, so we'll sneak that in here. Okay. So my interval, I'm going to go from -1, x plus 2, less than positive 1, subtract 2 from both sides, so -3, less than x, less than -1. And now we'll check those endpoints. So checking -3. So back up in my series up here. I'm just writing it down. So replacing the x with the -3. So I get -1 to the n. N equals 0 to infinity. Okay, -3 plus 2. So I have an alternating series because look what, so I have the -1 raised to the n. So this is going to be alternating, but, right, it's times n. So if you just think about what those terms are going to be, so if n equals 0, I got a 0, and then I get a n is 1, a -1. If n is 2, right, I get positive 2 minus 3, you got the pattern. So this, my nth term isn't going to 0, so the -3, not included. And then checking -1, I'm going to get n to 0 to infinity of n. And then I've got -1 plus 2, right, to the n. So that's just going to be a 1 to the n. So this is just the series n equals 0 to infinity of n. That definitely dives. So we're not going to include the -1 either. So my interval of convergence is going to be -3 to -1. Okay, let's do one more example. Okay, so here's my series, right? Centers at 3. Centered at x equals 3. So ratio test. So rho equals limit. N gets big. So that n plus first. So I have 7 to the n times 7. Get my absolute values in there. N factorial. Remember the exclamation is factorial. So that's going to be, right, so n plus first. It's n plus 1 times n factorial. And then I have my times x minus 3 to the n times x minus 3. Okay, I'm going to grab my white out so that I don't have to move that. Okay, so there we go. Gotta love the white out. Okay, so there's my a sub n plus 1. Now, a sub n, remember I start on the bottom and then go to the top because I'm flipping it. So here's, right, this is just my a sub n. So I'm going to have 7 to the n times x minus 3 to the n. And then n factorial pops up top. Okay. Cancel the commons. And there's a lot of them. Okay, now rewrite because it's going to be a lot easier. Rho is the limit, n gets big. I've got a 7 on top and x minus 3 on top, and n plus 1 on the bottom. Okay, I want to know for what values of x, remember, it's x that we get that we're controlling. And the idea is, right, when we get to finding these polynomials that fit functions, right, we're going to like expand around a certain x value. right? And so we want to know how close to that x value do we need to be for our series to be valid, to like actually be worth using. So for what values of x does the inequality hold? Okay. So, but we're also looking at the limit. So as n gets big, think about it, as n gets big, this limit goes to 0. Okay. And 0 is always less than 1. It converges, that we say it converges for all real numbers. So the radius of convergence is infinity. In fact, you might see some places r equals infinity. And then the interval of convergence, but it's just the set of all real numbers, however you're going to write that. Okay. So something that you might think about doing on these is right before you take your limit, if having that x minus 3 on the inside is kind of bothering you, since it doesn't really have anything to do with the n, you can kind of factor it out as you take your limit and then bring it back in when you want to solve your to find the interval. Okay. All right.